Okay, this video is about U substitution when you're doing integration or finding antiderivatives. And so what I've done here is just reminded us of some of the rules, the basic rules for antiderivatives. So if you're trying to find the function whose derivative is k, just some constant, you tack on a variable x or whatever variable it's oh, this is of t. This doesn't make any sense. Let me make these x's. You tack on the variable to make it, because the derivative of kx would just be k, and the derivative of a constant is 0. So we always have this constant because we don't know exactly what the function is unless they give us extra information. So what I'm going to do here is practice with these problems, and then we'll do like a couple of examples. So number 9 goes like this. If we're going to find the antiderivative of 4 times 2x plus 3 to the 4th power, what we'll do here is we need to let u equal to something, because this is very complicated, and if we were going to do it by methods we already learned, we'd have to multiply 2x plus 3 times 2x plus 3 times 2x plus 3 times 2x plus 3 and get it all in power rule, and then take the derivative. But that takes a long time, and there's a lot of room for error. So for number 9, let's do this. Let's let u equal to 2x plus 3. And then what you do is you take the derivative of both sides. So the derivative of u would be called du. And the derivative of 2x plus 3 would just be 2 dx. So you sort of take the derivative of u with respect to u and of x with respect to x. Now the deal is we need to rewrite this integral totally in terms of u, exactly, accurately, the same thing. So this 4 is a constant. Sometimes I like to put my constant on the outside of the integral sign. It doesn't matter. But now I have to find a way to write 2x plus 3 to the 4th. But u is equal to 2x plus 3, so I'm going to write that as u to the 4th. Now the only thing that I haven't represented is dx. So right here, I can solve for dx simply by dividing by 2. So if I divide both sides of this by 2, I get 1/2 du is equal to dx. So I need to put dx here, but it turns out it's equal to 1/2 du. So I can put 1/2 du right there, and that's my dx. So I've totally rewritten this integral in x's in terms of u. So now I just need to integrate this, which is much easier. 4 and 1/2 are constants, so I can multiply 4 times 1/2, which would just give me a 2. So now I'm just going to integrate u to the 4th du. And when I integrate this, u to the 4th becomes u to the 5 divided by 5, and I still have this 2 here, plus a constant. So this is 2 over 5, u to the 5th plus a constant, but I need to put it back in terms of x, so this is really 2 over 5 times 2x plus 3 to the 5th plus a constant. So that is an example of u substitution. So let me go again. Let me do number 11 here. Number 11 would look like this. We're going to integrate 2 over 2m plus 1 cubed dm. So do you see how they had the dm in the numerator? I wrote it beside. This means the same thing. Here I'm going to let u equal to 2m plus 1. Du will then take the derivative with respect to u, take the derivative with respect to m. The derivative of 2m plus 1 would just be 2 dm. All right, now I try to rewrite this in terms of u. This 2 is a constant, so I'm just going to pull him outside. I don't want to look at him. So I have 1 over 2m plus 1 cubed, but that is the same thing as u. So I have 1 over u to the 3rd power. And now I just have dm. But dm, if I solve for dm, because I don't want 2 dm, I just want dm. I can solve for that. But so by putting down 1/2 du times 1/2 du, this is my dm. This 1 over 2m cubed is this, and this is this too. So everything's represented here. A constant times a constant, I can multiply those. So 2 times 1/2 is just a 1. So really I'm integrating 1 over u cubed, which is really the same thing as u to the negative 3 du. Let's integrate this. This becomes u to the negative 3 plus 1, which is negative 2 divided by negative 2 plus some constant. Or this is negative 1/2 times u to the negative 2 plus a constant. But instead of u, I'm going to put in my original 2m plus 1. And this is the answer for 11. Okay, let's look at, how about 17? Number 17 is the integral of 3x squared e to the 2x cubed dx. Let's let u equal to 2x cubed. Then du becomes 6x squared dx. All right. Okay, I have to, this 3, I'm going to put him out front. Okay. I have to represent e to the 2x cubed. I get that part by writing that as e to the u. All right. Now I need an x squared dx. I have an x squared dx, but I have to divide off the 6. So 1 over 6 du gives me x squared dx. So by writing down 1/6 du, I got the x squared dx. So now I can integrate this. 3 times 1/6 is really 1/2. The integral of e to the u is e to the u plus a constant. So this becomes 1/2 e to the 2x cubed plus a constant. That is 17. All right, let me see. What about, let's do 21. The integral of e to the 1 over x squared d, I'm saying x, these are dz's. Let's let u equal to 1 over z, which is really z to the negative 1. All right, so if we do that, take the derivative over here, we get du. Take the derivative of z to the negative 1, we get negative z to the negative 2 dz. If we need to rewrite this guy, e to the 1 over z is the same thing as e to the u. But now I need this z squared is 1 over z squared dz. I need this, which is this, which I have right here, except for that negative. If I divide both sides by negative, negative du is positive, or 1 over z squared dz. So this is what I need to represent, and I can represent that by writing down negative du. So negative the integral of e to the 1 over z d, I'm sorry. Let me do this again. If I integrate e to the u du, I get e to the u. So it's going to be negative e to the u plus a constant, or negative e to the 1 over z plus a constant. All right, so that is that. Let's do the very last one on this, 23. The integral of t over t squared plus 2 dt. Then we're going to let u equal to t squared plus 2. du is equal to 2t dt. All right. So I have to rewrite this in terms of u. So this is going to be the integral of 1 over t squared plus 2 times t dt. This is the same thing. This is just helping me see what I have to do. To replace it with u's, this is 1 over u. 1 over u. T dt is what I need. I have that here. If I divide both sides by 2, I get t dt. So by writing down 1/2 du, I get that. Well, if I'm going to integrate 1 over u du, that is the natural log of u plus a constant. So this becomes 1/2 the natural log of t squared plus 2 plus a constant. And so that's how you can integrate with U substitution. Now, I have posted the key to this worksheet, and so it's a lot of the same. So look at the key on Canvas and see if you have any questions. But this is kind of a talk on how you can do the nuts and bolts of U substitution.